Haha. So, I will start with this presentation. We are already late, so let's just start. So, just who am I? My name is Leonardo. I am part of the Linux network. I am one of those that started the Linux network in Florence. We have a small community network, and rather than that, I am a researcher at the University of Trento, and I do research on mesh networks and on community networks in general. So before we enter pop routing, I have some news that are very good for me actually, and I hope also for other people. We got a new project, a research project, approved in the last call ICT of H2020. It's a large research project. It will last for 3 years, and it researches on community networks. So we have some different partners from various disciplines. So we want to make interdisciplinary research. We have UPC, we have Trento, we are the coordinators. We have the University of Westminster, we have Panos here from Nethood, that is an association from Zurich. We have a university from Greece and from France, and UPC from Barcelona. And we will do a lot of things that deal with community networks on various aspects, social, technical, legal. And so I hope that you will hear, we have to interact. Oh, thank you, Roger. We have some leaflets there if you're interested. Grab them and spread the news. Basically, in the project, we have to interact with community networks. We want to study how they are organized under a social point of view, how we can try to mix the analysis of the network with the analysis of the social network. What are the evolution model that they have? What are the governance model that they have? What are the models that scale, the models that do not scale? It's a very complex project. And I hope we will do our best to deliver something to the community networks that they can actually use, not only technically, because there has been already enough research project on technical stuff on community networks like Confine, Community, and this is another kind of approach we wanted to give, try to mix things that we believe are important in community network, which is not just the technical stuff. So another good news is that in Trento specifically, Trento is a city in the north of Italy, we are hiring people, 2 people on this project. So we have a PhD position that we start after the summer, and then we have 1 postdoc position or equivalent experience, which means that you have to have some research and development experience. And we are looking for people to work on this research project. So if you like to, if you want to do some research, applied research, and you want to stick in the environment of community networks, then you just contact me and I will be around. Personally, I do research on community networks, which means that I do applied research, and research is not the same thing that, it's not what everybody wants to do, it's what I feel like doing. It is nice, and if you like to work on community networks and you have the idea that staying at the university and doing research is good, and you want to be involved in the community networks, we will always be at the Battlemesh, we will try to be in other meetings. If you want to work on this under a research point of view, then this is a good chance for you to get involved. The call is completely open, so I'm not giving you this information just to turn you down when you apply, so we don't have somebody that must win, of course. So feel free to ask me all the questions that you want. Check the website and get in and make your idea. So, pop routing. Basically, a couple of years ago, I did a presentation at the Battlemesh, and it was also about amperes. Amperes are one specific feature of OLSR that substantially they select some kind of a subset of nodes in the network to produce the, how do you say, the, 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 control packets, TC packets that are spread around the whole network. And this is a feature that, to my knowledge, has never been used that much because there are various problems related to it. But the point of that feature was, if you want to have routing, you do not have to switch on the signaling, the control messages on all the nodes in the network. Most easily, if you are a leaf node, then it's not needed that everybody knows that you are alive. Like if you have your neighbor is sending information that tells that you are alive, this is enough. And MPRs are a binary decision, so there are some nodes that actually send the control messages and some other nodes that do not. So I started getting interested in it, and I got to the solution, to the point where I thought that you do not have to have a binary decision. You can have a continuous space of solutions where some nodes, they send TC message. I'm referring to OLSR terminology, but this could be used for other protocols. There can be nodes that send TC messages very often, and others that send TC messages once in a while and very rarely in time. Basically, when you want to set this specific timer with which you generate the hello and TC messages, this is, I think, the default from the RFC. And I mean, how do you set it? How do you know if this is too slow? Is you're generating too much communication? You're generating not enough communication? It depends on the network, basically. And so the point is, how can we set these timers in an automated way so that you do not have to decide based on some presets that may not fit your own network? And this is all what it's all about. It is a research project, so we have published the paper, we have the theory. I have been doing an implementation in an emulated network with some limitations. Now we are going to implement it on OLSR. Gabriel is here. He got Google Summer of Code for implementing this on OLSR version 2. And so hopefully next year we're going to have something running on RealNet. So we hope to have it, to have something testable now, but this was not the case. So basically, well, okay, I will just spare you a lot of things, but let's say that you have, do I have a pointer here? Aha. So let's say you have your network with n nodes, n links, and the neighbor per node. Then you send this number of hello messages per second, if this is the timer, the hello timer, and this number of TC messages per second, if this is the number of link, this is the number of nodes, and this is the timer. So basically, the number of messages that you have on any link increases linearly with the size of the network, which is something that, with these numbers here, gives you something like about 20 TC messages or all messages per second per link. Here, I'm not counting aggregation. So OLSR does some aggregation of the messages, so it reduces the contention time and so on, but this is just like, the principle is valid. So, okay, why do you want to have it? I mean, these are known concepts, I just review them. Why do you want to have more often or less often control messages? Let's use this network. This is a very simplified example with some details that I omit compared to real OLSR, just to make you understand. So basically, this node breaks, and you have a route that goes this path, from 0 to 4 and goes this path. So what happens at time 0, the node breaks, and then this node stops sending hello messages, and these two nodes here, they have to wait, like, depending on how OLSR is configured, but for example, 3 lost messages before they realize this link is broken, and this is true for OLSR or any other protocol that I know. Then what happens, that this node now, he knows that the link is broken, so at detection time he knows that the link is broken, and he flips his route. So now he knows that this route is not available anymore, so the route he knows goes this other path, which means that you have a loop here, because this node still believes that the shortest path is on the other side. This is loops. Then this keeps going on as soon as this guy does not generate another TC that says that this link is not is broken, so everybody should root on the other side, or this guy does the same. So everything stays broken as long as somebody does not generate a TC. So you have detection time that depends on the hello timers, and you have a propagation time that depends on the TC timer. Whether it is 3 or whatever, 3 lost messages, 5 seconds, it's not important. The point is that it is linear with these hellos, with these timers. Okay, the loop here, it is a simplification. You don't always have a loop. I think you have the necessary condition for you to have a loop is that when a link breaks, the new route that this node decides to use, it must be at least 2 units larger than the previous one, assuming that we have like 1 unit of weight for each link. If this is not true, then you may not have a loop. So this is not always true, but it can be true. Summing up, if you use the default timers, you have something like this, like the network can be broken for tens of seconds, depending on the configuration that you have. Seconds, tens of seconds, and it depends on these values, on the HT and the hello timer and the TC timer. So this is why you do not, you would like to have fast generation of control messages because you want to converge faster. On the other hand, you do not want too many messages because they will generate a lot of overhead. And also they will trigger a lot of recomputation of routing tables and so on and so forth. All this that I have said can be with some modification applied also to some distance vector protocol, if you exclude the loop and something like that. So you need a trade-off. And the point is, when you want to find a trade-off, I started from 2 observations. First of all, that there's no need to set TC and hello timers at the same value for all the nodes. In fact, the network works even if you set them differently. Hello and TC messages, they include a timer that says how much the message is going to be valid. So the receiver, he knows when he will probably receive another one. So he can detect the loss of a message. The second point is that not all failures are equal. So if this node fails, well, nobody cares, basically. It is not carrying any other route. If you have traffic that is directed here from other nodes, since node has failed, the traffic is already not working anymore, the node, the link, or whatever. And so we may try to find a solution in which you want important nodes to generate control messages with a higher frequency, and nodes that are on the periphery to generate control messages with a low frequency, which is something that is, in a binary fashion, is what NPRs do. If you're not an NPR, which means that nobody depends on you, then you do not generate control messages. If you are an NPR, you generate control messages. Here, what I'm trying to do is, I don't want, as I say, the binary value, but I want to distribute the frequency with which you generate messages linearly, depending on your position in the network. But the point is, how do we define an important or non-important node? And the answer is, there is this thing here that is called betweenness centrality, that is something that you can compute on any graph, and it's simply the fraction or shortest path that pass through one node. So if you actually are relaying somebody's traffic, you have some importance. If you are a leaf node, you have 0 importance. If you are somewhere close to the leaf node, you have less importance. This is a basic model. Then you have gateways, you have other things, and we have to work about this, but the theory, it's still, I hope, valid. I hope it's valid for you. I mean, I want feedback to understand if this makes sense to you all, apart from writing papers. So the point is that if you can compute your betweenness centrality, that is the number of shortest paths that pass through you, whether the graph is weighted or unweighted, it doesn't matter, then you know how important you are. And if you want to do this on OLSR, for instance, what you have to do is that every node needs to know the full network graph. So this, as it is, works on link state protocols. And every node will have to compute the centrality of every other node, which is pretty intensive, but this is what we are working on now. And then, if you're in the center of the network, you can be loud. You can generate messages with a higher frequency. If you are on the periphery, you will not be loud. And that is why it is called pop routing, because it resembles the equalization presets of pop music in music players. When you have something that you consider it's cool, you also have to find a cool name, or nobody will remember about this. Everybody remembers about fisheye because it has a cool name, and it works so-so. So I will spare you the math. If you want, you read the paper, and there is an explanation why it's like this. But I made a small model, theoretical model, that tells you that this is the best trade-off. What do I mean with the best trade-off? It means that given the amount of control messages that you generate with fixed timers, and this constant here includes also the timers, if you want to generate the same amount of messages, but you want to distribute the frequency differently in the network, these are the values that will actually minimize the convergence time of routes with that given amount of messages you generate. So if you configure, if you read the paper and you read the constants, basically this means that this network will generate the same amount, global amount of control messages as standard OLSR with the default parameters, but the convergence time when you fail, it's shorter here. I always refer to failure because it's easy to understand, but if instead of fail, you just like a link degrades dramatically, it's the same. So it's convergence time when the network changes for some reason, when link changes for some reason. And, okay, these are, I have implemented this on an emulator where I run OLSR. I configure OLSR with the timers. I pre-compute the timers given a certain topology, and I configure the OLSR with pop routing and without pop routing. These are three network topologies that I got from a past analysis. So they are real networks from, I think, from 120 to 240 nodes. And this is the average decrease in the convergence time when you apply pop routing to hello messages or to TC messages. Those two things do not sum up because they are interrelated, but they have a relation. So basically what I say here is that in average, you will have a convergence upon failure that is 1/4 faster than with standard OLSR. Now, I don't want to go too much into details, but this is the average, which means that the nodes that are more central will converge even faster. Basically, I want to keep the same number of control messages, so if some node converge faster, means that they send more information around, which means that if I want to keep the same number of messages, some other nodes will have to send less information. So the nodes that are central converge faster. Nodes that are in the periphery, they converge slower than they would converge with standard parameters. But in average, everything improves. And in the center, it will improve more than this. Am I making the point somehow? I see that you are particularly interrogative. So if you have questions, please stop me. I think I'm giving a lot of things for granted because I'm sure you know many things.
thinking on what you said about the peripheral nodes, that they converge slower, but I was thinking on typical topologies, also if a peripheral node hasn't converged, it's not a problem, because it's very probable that the route, the table of routing you have, while it doesn't have converged yet, and the table of routing you have when you're already converged is enough coherent. The routing table doesn't change too much in a peripheric node.
Yeah, I think I said converge. I mean, when a node that is in the periphery fails, then all the network converges slowly. When a node that is in the center fails, all the network converges quickly. I do measure this with, I have my emulated network with this topology. What I do is, for each network node, every 100 milliseconds in the emulated network, I dump the routing table. Then I make one node fail, and then I keep dumping the routing table. Then offline, I got all the routing tables, and for each time in which each timestamp, I compute all the shortest path, and I navigate virtually in the routing table that I had, that I dumped before. And I check which are the routes that are broken, which are the ones where I have loop, and I check for how much time this lasts. And this convergence metric is complex to explain now, but it's actually the number of routes that are broken multiplied by the time for which they are broken. And the area of that curve is 1/4 smaller than with standard OLSR. And yeah, now this works a lot of, it works pretty good. And I also checked that in my experiments, effectively, the number of control messages is comparable. It's more or less the same with standard numbers with default values or with pop routing. Now, what you have to do if you want to actually do this for real, you need to compute the betweenness of every node. And you need the degree of every node. If you go check the formulas, you need to computing your own timers dynamically at runtime, you have to know the betweenness of all the nodes and the degree of all the nodes. To do this, there are three approaches. The dummy approach is you compute all the shortest path from each couple of nodes, and then when you have them, you check in how many of the shortest path you are in between. You are part of the path. And you do this for all the path and for all the nodes. And this is dummy. You can do something better because you have, you can actually compute the betweenness of a node while you compute the shortest path. So you run Dijkstra, or Bellman-Ford if whatever your network is, and while you compute Dijkstra, you accumulate the centrality of each node. There is a paper that says that. It is like standard literature. And this, it's a bit easier. And then there is a better heuristic approach. And basically what you do here, I don't think I have a figure, no. What you do here is something like this. Oof. So you have a network, whatever, and you start dividing it in be-connected components. So these are components that are connected with just one link, basically. So you do this, which is linear with the number of nodes, and then it is much easier to compute centrality on each component, and then sum up the centrality for one node that stays in many components. Now I'm spending my time with this because the good thing is that if you take real networks, like at least looking at the topologies that I know, that I have analyzed, when you split a network in connected components, since our networks are not really well connected, not really dense, the network gets split in a lot of separate components. So this heuristic here works pretty well. And pretty well means this. That's this for the 3 networks I mentioned before. A student of ours implemented on a Ubiquiti M2. She implemented the heuristic and she ran it on a topology that is of this size. So this is not running on real networks, it's just to see how much it takes to compute the betweenness centrality of every node on a real device. And these are seconds. The red bar are the one with the heuristic betweenness centrality. These are seconds, which means that, yes, it takes like few seconds of your CPU, which means that it is reasonably doable, but you cannot do it in the protocol, in a single-threaded protocol. You cannot stop OLSR for 7 seconds just to compute centrality. So what we are trying to do is 2 things. First is like developing another daemon that should get the topology and compute it as a separate process so that you don't clog the same routing protocol. And then the other thing that I want to do is trying to understand how often you have to compute the centrality. I have dumps from Linux, from Freifunk, for like 1 week of evolution of the network. And my first measurement tells that you could actually compute centrality once per day. It doesn't change that much. The bad thing about this is that sometimes the network changes dramatically because somebody adds a link or there is a link that is flaking. So when the network changes dramatically, if you compute it once per day, you stay 1 day with sub-optimized hello and TC timers. One thing I didn't say is that even if the network, even if you do not recompute betweenness, the network still works. I mean, it's not that it stops working. It's just using parameters that are not optimized. Switch it on.
Decreasing the convergence time. Yep, and that's your objective. You do it by knowing which nodes are central and which not. What happens if, due to link breakage, some nodes which were previously not relevant become very relevant, and those which were relevant don't have the good link anymore and become leaf nodes? Wouldn't this lead to the problem that you optimize, or you have told all nodes, here, look at these nodes, they're relevant, and these nodes may still update their TC messages very often, but you don't get them there, let's say they're dead. And those which are now relevant, because the poor links, let's say, with which they have been connected to the network, they were not used before, but now they are the only links left.
So if I get your question, what happens when the network changes for some reason that the array of centrality values changes a lot? So some node that was very central becomes very peripheral or vice versa. The point is, centrality is not something that depends only on you. It depends on your position in the network. So our network are mostly planar network, which means that well, if you take a graph, a bunch of nodes, random nodes, and you connect them randomly, you have a lot of crosses between the links. Our networks are physically bound to physical locations. So you can represent them quite well in a plane, because they are on a plane, with not that much of link interfering each other, which means that you have a good notion of who is central and who's in the periphery. It is pretty clear. If you take an Erdős graph, a random graph, it is not clear who is in the periphery and who is in the center.
But I understand.
Okay. And the point is that centrality in such network do not change dramatically if you add or remove one link. If you want to add or remove, if you want to change dramatically centrality, you have to add or remove one link that changes dramatically the average distance from one node to the other. So if your network has an average number of 5 hops, then let's say that you add a link and this effectively brings it to 3. So you're actually cutting into all the length of the routes, then you change a lot the centrality. But this does not happen often. And what I'm trying to do here is exactly to find out how and if this happens. So I'm trying to collect snapshots of networks so that I can analyze them and I can try to understand what is a way to, well, I don't think that there is like an optimal number that for each network, but something that you can, for instance, you can actually pre-process the network graph and understand if things have changed a lot or not, and see if you have to recompute or not. But the thing I want to stress is, even if you are with an optimized parameters, everything keeps working. It's just that some node that is now very central is still sending control messages slowly. And yeah, what about if you do not know the whole topology? Okay, correct me if I'm wrong. In OLSR, you will actually find out that the link is broken when you receive a TC. And you receive the TC from neighbors of the node that is broken. Let's stay with the example of a failed node. Which means that from the moment when a node realizes that his neighbor is dead, to the moment where everybody knows that the neighbor is dead, it passes an amount of time that is proportional to one TC timer. Now, in distance vector, it should not work like this. Like, when something breaks, then the neighbors will sense that it broke, but nobody will switch their routes as soon as they don't find another route from somewhere else. The problem is similar. Like, if you formulate it, it's similar. So even if you have no loops here, the math that I showed you before, it should mostly work the same way. But what you do not have in a distance vector is the full network graph. So you cannot actually compute betweenness on all the nodes. And here you have two ways. First, you share the network graph somehow. I think most of the protocols, they already share the graph to draw the graph or something like that. And as I said, since this doesn't have to be computed every second, but it can be computed every hour, you don't have to update it every second. The second point which we are working on is there are distributed ways of computing centrality. They do not require more control messages, more messages compared to what you already do for routing. So there should be a way for every node to compute its own centrality, just watching the routing messages that pass through him, even in distance vector protocols. Of course, the problem is then you only know your own centrality, so you have to find a way to spread it out, like adding this field to the OGM or whatever other broadcast packet you have in your network. And I think I am finished. Yes.
I remember your earlier, I came a little bit late to the talk, but I remember your earlier presentations of the centrality ED. Why do the rest of the network need to know my centrality? Because if you use it to control the rate of control messages generated by my node, everyone else should not care. If my centrality goes down, maybe then I reduce the number of updates I present and the rest of the network will notice because it gets less updates.
You have to scale it. Like, if you want to keep the number of messages, control messages that generate constant, then you have to scale your own generation based on the distribution of the other nodes' frequency of generation.
Could I just count?
Count what?
Count the number of all routing messages on average. If I count the number of routing messages coming in the last hour and say, okay, my centrality goes down, I do a little bit more, and the rest would maybe get a little bit up.
But then you introduce a control loop,
Yeah, but
which you have to stabilize. You have to be sure, because you are measuring centrality based on the TC that you receive. You change your generation frequency, which means that you change the perception of the other nodes.
or you need just a good mapping for your own centrality to a TC rate, then you cannot guarantee that the data rate, that the package rate of updates stays stable, but it should be reasonable self-tuning. Just a local, instead of comparing with everyone else's centrality, just doing some local mapping. Centrality directly mapped to local update interval.
I mean, the principle, centrality goes from 0 to 1. So 0 is 0 centrality, leaf node. 1 is I am in a star network and I am in the middle. So the point is, when you want to tune your centrality, you have to know which is the range. When you want to tune, your frequency, generation frequency, you have to know the range. The range is from 0 to 1, but in a specific network, you don't ever have one node with one centrality. So you have to know where you are. You may have 0.2, which in some network is really high, and in some other network it's in the average. So that's why you need to know all the centrality values.
As the slide before, you were asking for routing topologies. And I would provide my routing topology, because I'm quite interested in how to set these values. How to set the TC and the hello values. Right now, what I'm doing in our network, I set this based on the amount of messages that goes through the backbone and through the nodes. So it's like a manual trade-off between control messages I think are enough and still needed, but without any glue of, okay, if this is an important node, it should be a bit more, as the effect if this one goes down is higher compared. So I would like to, if you could imagine something like you offer a service, I upload you my topology, and you provide me 2 numbers for each node that I use as a configuration. I would be happy to, if this is possible. So I think for 200, 240 nodes, it doesn't matter what kind of centrality calculation you use on your machine then.
Excuse me?
The centrality calculation would be done centrally on your side. As we have a static network that I design, I have a feeling of centrality changes or
I
not.
can just show you the code and
Run it somewhere, zack, form. What you need? Could you handle the dot file from OLSR? You just... what's the concrete format I should send you?
I think, do you have a NetJSON?
Sure.
I think we can use NetJSON. Do you have many dumps? Like, do you have an history of dumps, or you can start?
I can produce whatever is needed.
Yeah.
That's
Cool.
the question. What you need that I send, and then
I need dumps. The highest frequency you can provide them, the better it is. Even if probably we don't need like 1 dump per second. It's like I have dumps once every 10 minutes for Funkfoyer networks, and I still have to analyze them well in the evolution. But as I said, my impression is that they do not change dramatically from 1 hour to the other. So if you give me dumps every 10 minutes for 1 week, it's okay.
But wouldn't it be enough to give you 1 snapshot of my topology?
This is, of course, but I was answering the question that I asked myself, not the question that you answered.
Okay.
So, it is enough for doing one-shot calculations,
Yes.
so that I give you the timers.
Exactly.
What instead I'm interested to is to find a way to fine-tune the logic with which I recompute the timer. So I need sequences to understand how the network changes.
That highly depends on the network, blah, blah. What's the dynamic of that concrete network?
And so the complete answer is I can just give you the Python code that I use to compute the timers.
Yeah, that would be cool. As I'm, right now I do this by, 40 kilobytes per second, OLSR traffic is fine in my backbone. 140 is too much, so I tune those values to be under somehow network management perspective below something.
Yeah.
Just a sentence to this, as you refer to errors, I think what might be a bit problematic is if you consider also, and maybe it's centrality changing, mobile stuff. Because if a lead node is mobile, you have a different interest in being up to date with the topology if you roam, as if you would be in a somehow static setup, no? Where the centrality is enforcing frequent updates do have more impact to others than not, but mobility would introduce a different interest in
Mobility would spoil everything, basically. With the mobile network, where the topology changes often, you do not even have a concept, well-defined concept of centrality. You have a concept of centrality defined in a certain moment, but the effect of your tuning do not apply to that moment, because you start generating messages like for an event that will happen. So again, you have a loop, because centrality changes, you tune your hello and TC timers, but in the moment you may need them, then centrality may have changed. So in mobile networks, I have no clue how this would work.
And one last question, very, very last question. Because you showed us you were able to bring down the convergence time by force. But what means that in absolute values? It depends on the network topology. Let's say you imagine 100 nodes and some kind of topology, don't know, critical topology, 2 passes to the gateway, and you have default OLSR values. You use one configuration for all versus your configuration, you are force time faster. Is force time faster than in the order of...
I'm reducing on 1/4. Or
yes, on 1/4, but it's like the absolute time. Are we talking about important link breaks, all other suffers 10 seconds or a minute, and you were able to bring this down to 4 seconds? Or
but that depends on the default parameter.
Yes, I know. But what's like the topologies you had? What would be an extreme case where you say, okay, if this link breaks, the standard values will take you a minute to converge. So what is a typical convergence time you see?
The largest in the worst case, you need like 3 hellos to detect a link break, I think. Yeah, with default settings, I think it's 3 times. 20 seconds validity time. Oof. So, to detect a link failure, then you have to generate the TC that will propagate the information to everybody, which will take, depending on when you detect, but it depends on the way you configured it. So tens of seconds. That's the
tens of seconds
in the worst case. 25, 20 plus 5, yeah. But the point is, I did not have an answer because this is like the worst case for the worst route.
Yes. But if the worst case for the worst route is 1 second, I don't care if you optimize something. That's why I'm asking.
If you want to have 1 second, you have to detect it in 1/3 of a second, which means that you have to send hellos every 50 milliseconds, which means that not only you have a lot of load, but that your router is always recomputing routing tables. So there is also this thing that the more frequently you send a signaling, the more you generate events.
Thank you.
More questions?
Any other? Doesn't seem so.
Okay, so we have a few more slides from Gabriel that he is going to implement this, and he wants to show you how it will. Very long, sorry.
Okay, so I won the Google Summer of Code for implementing this program in C++. Now we have an implementation in Python, but it is centralized and it can't run in the nodes since we don't have the interpreter there. So our idea is to write it in C++ and yeah.
Typically, OpenWRT nodes don't have the standard library for C++ installed. Nobody is, if you look who's using UClib++ or muzzlelib++, you will notice the default installation does not. So doing it in C might be better because you're not drawing in half a megabyte of standard library in addition to your program.
Yeah, but we must calculate the centrality and everything, and rewrite everything in C will be quite long. So we use the Boost library that already implemented.
How large is Boost and C standard, C++ standard library?
Maybe you know that?
Sorry, I'm the responsible for this. No, the point is that if you want to do the heuristic algorithm, you have to have Brandis, the algorithm for between the centrality implemented, and you have to have the algorithm for identifying the bconnected components, which are already implemented in Boostlibs. I have a student that did use it and did port it to an Ubiquiti M2 with OpenWRT trunk. No, I think it was 15.5. So it sticks there. Now, probably we could do it from scratch in C. I think it would take quite a while because the algorithms are pretty tough. And so we decided to go this way for the moment.
Okay, so we wanted to develop a package for OpenWRT or LEDA now to do this. And let's see. We want something that is independent from the routing protocol, so we can switch it for other protocols like OSPF or OLSR1. And we wanted to use the NetJSON formsat. This is the architecture that we thought, and we have the routing daemon. In this case, is ONF, or we can also have OLSR1. And we have a plugin that provides topology. In this case, through the Telnet plugin. And in our daemon, we use another plugin to interact with it, so we can keep it independent. And we just read the topology and compute the timers, and then push the timers value to the plugin. In the case of OLSRD2, we can just use the Telnet plugin. In another protocol, for example, OLSRD1, we must implement it. Right? So this is the interaction diagram, if you want to see it. It's quite simple. And yeah, we ask for the topology to our plugin. It connects to the Telnet plugin and use this command, NetJSON graph. It returns the graph, and we use it to parse. We parse it and we use it to calculate the BC, and then we use this value to calculate the timers. We push the timers back, and we are done. We have to do this many times. We have to figure out how long, and yeah. This is the same for OLSR1. And yes. So this is what we want to do. Transform the program that we already have. It's named graph parser in a library. Define the NetJSON extension for a between centrality and maybe also for the degree, so we can push them inside. Write a daemon with the ONF plugin. Yep. Then the stable release, and maybe a plugin for OSPF. And yeah, what we would like to do later could be use the instance vector protocols, as we said before. We can do that with Batman, probably using Alfred, since it collects the topology. And then if it's possible, I don't know, with BMX or Babel, then it's finished.
Just one thing, still about the implementation. On paper, this works pretty well, and there are some glitches and some things that must be. We need some heuristics. For instance, in some cases, the computation that you do, they will lead to have a TC frequency that is higher, the generation higher than the LO frequency, which doesn't make that much of a sense in the same node. So we wanted to go to have something that we can run on real networks, like we have in Linux in Florence. We will deploy this in a small network so that we can start actually checking for these kind of things and debugging. And so we needed something that was going to work in a reasonable time, in the time of a GSOC. And that's why we went for Boost and all the other things.
I don't see how you can benefit from this in distance center routing protocols. Because if you want, I don't see how you can benefit from this for distance vector routing protocols. Because if a central link goes down, then you might think, okay, routing updates from the central link must be propagated more often. But no, all routing updates are crossing or potentially crossing this central link must be sent more often, because it's those routing updates which trigger and control or and in the end ensure that routes are bypassing this broken link.
Okay, there are two things here. First is that you can, with the LO timers, this is working anywhere. At least for protocols that do not have like a request response mechanism. But if you are, for link detection, but if you are doing link detection with, yeah, but I mean, if you tune the frequency of the generation of LO timers like this, you would benefit from faster link detection on any protocol. This is.
Because it remains
less.
local.
It hurts less, this is true. The other thing is that when you are a node that is a central node, your neighbors are central too. Like, if you, centrality is something that, like if you imagine like a line network, then centrality goes like this. So if you have a high centrality and you break down, your neighbors also have a high centrality. So what you mean, if I understood, is that when the node breaks, it's not much important how his own centrality was, because he will stop sending messages anyway. But the point is how his neighbors are central. If they are also central, they are sending updates frequently.
I mean, if the neighboring nodes send their routing updates, are we talking about routing updates now, or hello messages?
I'm talking about TC or whatever.
So something global.
Yeah.
Which is propagated globally. So
yeah.
Routing updates in the distance vector protocol. Only those nodes which send routing updates then will be recovered.
Oh, excuse me, all this?
Only if a link breaks.
I cannot hear you.
Yeah. If a link breaks, if it's central. Only and then there are many routes affected, all routes that go across this link. And any of them can only be fixed if all those routers who send these routing updates for these routes send a new routing update. But it doesn't help to just let the neighboring nodes send new routing updates. It will only fix the routes to these neighboring nodes. But all the others remain lost.
Are you talking about like... I think I need a drawing for this.
We can do a drawing. Yeah.
But You're talking about like distance vector like Babel or
Like Babel, yes.
That's another story.
Like BMX.
But
Or like distance vector routing.
BMX, you send signaling messages, control messages that reach the whole network.
There are no control messages in that sense. You mean routing updates?
Yeah, and you send them periodically.
Yes.
So what happens is that somebody will switch to a new route if a link breaks because he receives an update from another route that works, okay?
Yes.
So the point you're making is this may not be close to the link that broke down. It may be somewhere else.
Yes.
Okay, I have to think about it. You're right in general. The point is that generally, if your network is dense enough, unless it is a nice ring, then when something breaks, you do not pass from a path that is completely another path. You pass somewhere close to the link that broke down, if the network is dense enough. And central nodes are the ones that are in the denser part of the network. So this is...
But the updates from the nearby to the central node don't change anything for the majority of the nodes in the network.
That's another point, because you can actually, you mean that the default route of a leaf node will not change if something in the middle of the network breaks down, because the packet will arrive there and will take another path.
It will get lost. It will run into the broken link.
I need to draw it down. Last thing I want to say is with this kind of technique, I think you can do a lot of things, not just setting the timers for the routing updates. For instance, BMX caches packets. So when you receive updates, you hold them for half a second or something like that. You can use this kind of, and this is bad, because propagation is lower. So if you want to propagate your, in my counts, I do not consider propagation time. I imagine it is simply quick. If you include propagation time, then you have more advantage in using pop routing rather than without propagation time. What you could do is, for instance, fine-tuning the hold time of the packets for central nodes. Now, if you have to hold them more or less, it's something that I still have to understand, but it's something that you use for this.
I agree here. I have a small question. Why do you say your subtitle was "Forget about timers"? But after listening to your talk, I think it's all about timers.
Yeah, it's forget about configuring your timers.
So, thank you for your talk.
Thank you.